All right, everyone. In today's session, we're going to go through assignment 4. It's a multiple linear regression using data from PISA 2012. And just to look back at the assignment and anchor us, so the first two items were more about things that you could read to help you prepare for this. So basically what we're doing is running a multiple regression where enjoyment of math, math career, gender, and PISA's measure of SES are being used to predict students' math scores. And in order to do this, you have to go through and dichotomize some of these items. The enjoy math one could potentially be left alone, but then you're making some big assumptions because it's only a 4-point scale. So changing that into a continuous scale brings up some potential problems. However, I've left that up to you to make a decision. All right, so if we go to SPSS, the first thing we need to do is dichotomize some of these things. So particularly the enjoy math variable, the variable for gender, and the math career variable. Like I said before, enjoy math might be able to be put as scale. I'm going to leave it as scale for this assignment and focus on dichotomizing these two things. So if you go to transform, recode it to different variables, and then in this little box that shows up, we're going to put the gender code, and I'm going to put an output called female. And the reason I'm choosing female is because I'm going to make female be represented by the number 1. So when we dichotomize things, we're putting things into 1s and 0s. Right now, female is 1 and male is 2. So after you type that in, click the change button. Oh yeah, and I've already got a variable called female. So I'll put female 1 for now. Then old and new values. We always want to start by making sure that anything that is missing in the system stays missing in the system. So click add, then it says system missing, arrow system missing. All right, then we want to make sure that females, which are represented by the number 1, so the old value being a 1, stays as a 1. So here you see it says 1 becomes a 1. And then if the value is a 2, we want it to be a 0, which will be representing the males. Click add, and then click continue. And once you hit OK, that is going to create the variable for female. Now notice that I'm not going to click OK because I've already created this, but when you do that, it will change this to be nominal by default. So you will have to change it to scale in order to use it with the multiple regression. Same thing for math career. Now math career, I put some codes in here. 1 is that a student wants to pursue math. 2 is that the student wants to pursue science. And what we don't have is how many students didn't select either of these options. We only know if they selected them. We don't know if someone doesn't want to pursue one of these two things. And we can't tell the difference between not checking a box and leaving it blank. So it's difficult to tell if someone just doesn't want to pursue either of these options, or they just left it blank for some reason. So that changes our interpretation later. Transform, recode into different variables. We'll put in the math science career variable. And here we can call it math career. And when you name the variables, there can't be any spaces in that variable name. Click change, old and new values, and this time, of course, we're going to keep system missing as missing. We want to talk to be referencing people who have a math career or who want to pursue a math career. So we're going to put a 1 is math career in the data set, so we want that to stay a 1, and we want the number 2 again to become a 0, because that represents that they would rather pursue science. All right. And then you would click continue. And once again, when that happens, it will put it at the bottom of your variable list. Make sure to change it to scale. All right. And then you want to check and make sure that these things actually were correctly coded. So to do that, go to Analyze Descriptive Stats and Frequencies. Frequencies report numbers of categories of things. So we just want to make sure that people who were originally coded as female ended up as a 1 in our new variable, so that they're all still representing a female. So in here, I will put the the gender and math career variables, and then go to the end and grab the new gender and math career variables, and then click OK. Now we want to make sure that this worked. So you can see here the gender variable. This is before we recoded it. We have 33,714 female. And then if we go down to the female variable, female represents a 1, 33,714, and the other number is 31,821, which matches the males. Math career, pursue math, 17,166. Pursue math and math career is 17,166. And then pursue science, 22,609. Science, 22,609. All right. So it looks like it worked. Now we're ready to run our multiple regression model. So go to regression, linear, and the dependent variable is PV1 math. And then we want to make sure that we put things in the same order that they were in the assignment. So the first thing that should go in is enjoy math, and make sure you change that to scale, or if you dichotomized it, also make sure that you put it in a scale and that you select the dichotomized version. And then we are going to put in math career, gender, and then SES. Math career, gender, which in this case we called it female, and the ESCS pieces SES measure. All right. If we want to see whether or not this was appropriate to run a linear model, we can look at the histogram and normal probability plot for the standardized residuals, and also look at a plot of the residuals versus the predicted value. In this case, the predicted value is the math scores, and make sure that there's no pattern in those residuals. We don't want to see a relationship between residuals and outcome measure. And then click OK. Give it a minute to run. And the first thing that comes up we see in the ANOVA table, statistically significant. F statistic is very large, 4,39,313 degrees of freedom. So once we reduced the data set by deleting people who didn't have full information on every variable, we went from around 65,000 to 39,000. So quite a few people were removed, and it's because of that math career variable. R of 0.493, R squared of 0.243, so only about 24% of the variance in math scores can be explained by this model that includes these 4 variables as independent variables. So it's not a great model, but it's not horrible either. If we go down to the coefficients, we can see that p-values all look like it indicates that there is statistical significance. T-scores are fairly large, except for this math career variable, which looks like the least impactful. So when we interpret these, so the math career variable, remember, a 1 means they want to pursue science, and a 1 means they want to pursue math. A 2 means they want, or 0 means they want to pursue science. So in this case, that 1 tells us that people who want to pursue a math career on average score about 2 points more than people who want to pursue science on the PISA math test. The problem with that is these scores have, for this particular subset at least, have a standard deviation of about 90 points and a range from about 85 points up to about 800 points. So a difference of 2 points, even though it's statistically significant, doesn't carry any meaning once you look at the context of what that 2 means. So it's statistically significant, but I would argue it's not practically significant. The same goes for these other values. Enjoy math. So, and enjoy math is an interesting one because 1 means strongly agree. So as the enjoy math variable increases in value, students enjoy math less. So that's why this is negative. We would need to reverse code this variable to get a positive value and a more direct interpretation. But basically, students who enjoy math more do have higher scores, but that differs by about 7 points. So about 28 points, since it's a 4-point scale, from difference between students who really strongly agree that they enjoy math versus people who strongly disagree that they enjoy math. That seems like it's better, but the increases in between are not very big. And then, of course, SES is the biggest impact. It has the largest t-score here, so the p-value will be the smallest, although we don't want to interpret that means that it's more important, but it does have the biggest impact on students' scores, the biggest effect. Looking at the residuals, we see that the residuals are normally distributed. The probability plot looks good, so and then here it doesn't look like there's any inherent pattern, that the correlation would essentially be 0. And if we double click on this plot, we can add a regression line just to verify that it does in fact have no relationship between, and this opens up and you just need to make sure that it says linear. And close it. You can see the line is here, and here's the slope on the x. See, it says multiply by x there. And this is a very, very small number, 1.98 times 10 to the negative 16. So there are 15 zeros after the decimal before you get to that first one. So essentially there's no relationship between the residuals and the predicted value, the math scores, which tell us that a linear model was appropriate. And there you have it. And in the next assignment, we'll go a little bit more into detail. The one thing I didn't include in the coefficients table here is the confidence intervals, which can help you get a better idea of how tight that effect size is in its range of possibilities in the population. And that is it for this. We would answer this question, whether it is enjoy math seems to be influential in students' math scores. The answer would be statistical significance would imply yes, but the impact is very small. So perhaps not any practical impact. All right, and that is it for assignment 4.